Okay, hi AP class. This is your lesson for Wednesday evening, September the 18th. We did part of it in class. It still takes a little bit of time to write out, so I'm going to do this pre-written and just walk you through the steps. So let's talk about why we did this. Up until now, what we've been doing when we've been computing the masses of molecules, the number of moles, the number of atoms, and so forth, we've been computing atoms and molecules and mass in atomic mass units. But we found that those translate directly numerically into the number of moles. Number of atoms and molecules goes straight to moles, the same numbers. And the mass, instead of being in atomic mass units for a single molecule or a single atom, is in molar mass for a mole. So if you multiply an atom by 6.022 times 10 to the 23rd, you get the same mass, except it's in grams. So instead, we're going to just skip over that step because we don't work with atoms and molecules in atomic mass units. So we're going to skip that step and just go straight to moles and molar mass, and it's computed exactly the same way. Then I'm going to add another additional function here, or additional function here that we haven't talked about, but that's used in chemistry, and that's percent composition by mass. It's how much of a molecule is made up of a certain particular element. So we'll get to that in a second. So here we go. So hydrogen, H2O, has 2 moles of hydrogen. We're not talking about 2 atoms anymore. We're just going straight to moles. So there's 2 moles in a mole of water molecules. There's 1 mole of oxygen, and that gives you 1 mole of water. So if you take the 1.01, that's the molar mass. That's the mass of a mole of hydrogen. And you multiply it by the 2 moles, you get 2.02, and this is in grams. So the mass of hydrogen in a water molecule is 2.02 grams. Okay, the mass of oxygen in a mole of water molecules is 16 grams. And if you add them together, 1 mole of water molecules is 18.02 grams. So now we can compute the percent composition by mass. So of those 18.2 grams, 2.2 of them belong to hydrogen. So if we divide 2.2 by 18.02 and multiply by 100%, don't use the percent function on your calculator, just multiply by 100 and then put the percent sign on at the end. You get 11.2%. So roughly 1/10 of a water molecule is hydrogen if you're measuring it by how much it is by weight, by mass. 88% of a water molecule is oxygen, as measured by the mass of the oxygen molecule. Excuse me, the oxygen atom. So those two have to total up to 100%. Okay, so now let's do one. We did this in class, so I'm going to walk you through it quickly. NH3 is ammonia. So there's 1 mole of nitrogen, 3 moles of hydrogen. When you put those together, you create 1 mole of ammonia molecules. So up here we have the 1 mole times 14.01 grams. And that's going to give you 14.01 grams for that 1 mole of nitrogen. Here we have 3 moles of hydrogen. You multiply 3 times 1.01 grams, and that gives you 3.03 grams of hydrogen. When you add these two together, you get 17.04 grams is the mass of an ammonia molecule. So over here, what we do is we are going to take the mass of the nitrogen divided by the mass of the entire molecule, multiply by 100. So we see that 82% of an ammonia molecule is made up of nitrogen. And 17.8% is made up of the hydrogens, the 3 hydrogens. And of course, these two total up to 100% right here. Okay, again, skip ahead or slow down and stop and pause if you want to review an explanation. Okay, next we're going to go to propane. So we have C3H8, so we have 3 moles of carbon. Those 3 moles times the molar mass of of 1 mole of carbon is 12.01 grams. So you multiply that, you get 36.03 grams of carbon. For hydrogen, if we have 8 moles, we multiply that by the mass of 1 mole of hydrogen, 8 times 1.01, and that gives you 8.8 grams is the mass of 8 moles of hydrogen. If you add these two numbers together, it gives you the molar mass of 1 mole of propane. and that's going to be 44.11 grams for 1 mole of propane. So again, we compute the molar mass the same way. It's the mass of the carbon divided by the mass of the entire molecule. If you multiply that by 100, you get 81.7%. So 81.7% of propane is made up of carbon. Same thing for hydrogen. You get 8.08 times 4 divided by 44.11 times 100%, and that means 18% of a propane molecule is made up of hydrogen. And you add those two together, and you get the total for the total of 100%. All right. Let's move on to the next page. And now we're going to do peppermint and vanilla. So what we have here is for peppermint, it's C10H20O1. So that means you have 10 moles of carbons. If you multiply that by the mass of a single carbon of 1 mole of carbon, 12.01 grams, you get 120.1 grams. For hydrogen, you have 20 moles of hydrogen. Each mole is 1.01 grams. So if you multiply that, you have 20.2 grams of hydrogen in a mole of peppermint molecules. Finally, oxygen is 1 mole. You multiply that by its molar mass, which is 16. Then these are the same as the atomic masses from your periodic table. It's just now we're calling them molar masses because they apply to a mole of the atoms. So 1 times 16 is 16 grams. You add all 3 of these up, and the mass of 1 mole of peppermint molecules is 156.3 grams. Okay, so the the percent composition by mass is done the same way. So it's the 120 right here divided by 156, our total right there. So that divided by that times 100 is going to say, so 76.8% of a peppermint molecule is made up of carbon. Same thing for the hydrogen, 20.02 divided by 156.3. So 12.9% of a hydrogen, of a peppermint molecule is made up of hydrogen. 12.9% of a peppermint molecule is made up of hydrogen. And finally, oxygen. There's 16 grams of oxygen. You divide that by 156.3 for the entire molecule times 100, and you get 10.2% of a peppermint molecule is made up of oxygen. And these numbers add up to 100%. All right, we'll move on. And now we're doing vanilla. Looks fairly similar. It's only different by a couple of carbons and quite a few hydrogens actually, and a few oxygens. But that actually yields an entirely different reaction with your tongue to give you a different flavor. So carbon, you have 8 moles of carbon based on this right here. You have 8 moles of hydrogen, and you have 3 moles of oxygen based on that. So again, we keep using the same masses over and over. So 8 times 12.01. So you have 96.8 grams of carbon in 1 mole of vanilla molecules. You have 8 times 1.01. You have 8.08 grams of hydrogen in 1 mole of vanilla molecules. And you have 3 times 16 for oxygen is 48 grams of oxygen in a mole of vanilla molecules. So we do percent composition by mass. This one is 96.08 divided by 152.16. And that times 100, that gives you 63%. So 63% of a vanilla molecule is carbon. Similarly for hydrogen, 8.08 divided by 152. So 5.3% of a vanilla molecule is hydrogen. And right here we see that 31.5% of the vanilla molecule is oxygen. All right, so that's how you compute percent compositions by mass. And from now on, when we do these calculations, we're doing it for moles, not for individual molecules and atoms. We're doing it for entire moles. All it does is change the unit of measure on the mass to grams. All right, let's balance some equations. And I've been having some problems with this system here today, so I just went ahead and wrote it out, and we're just going to kind of plow through this a little bit. Actually, I'll redo these because you need to see them work one by one. So we have lithium and nitrogen, and that gives you Li3N. Okay, we don't care about the states of matter. We'll get into that later on. Okay, so lithium. So we have a box with a lithium in it. We have a box over here with 2 N's in it because there's 2 nitrogen atoms. And we have a box with 3 lithiums and a nitrogen. So you can choose whichever one you want to balance first. I'll go ahead and balance lithium first. So we have 3 on this side. Draw a line so you don't get confused which side you're dealing with. I have 3 on this side of the arrow and only 1 on this side. So that means I have to draw 2 more boxes here. Okay, so now I balanced lithiums, 3 and 3. Now I'm going to balance nitrogens. I have 1 on this side and 2 on this side, so I've got to draw another box here to make nitrogens balance. But I have to make a photocopy of the box above. It's got to be exactly the same elements, okay? So now I have 2 nitrogens here, 2 nitrogens here. In doing that, though, I threw the lithiums out of balance. So I have 1, 2, 3, 4, 5, 6 here, and 1, 2, 3 here. So now I have to put them back in balance by adding some more lithiums. And you can see I have 6 lithiums here, I have 6 lithiums here, I have 2 nitrogens here, 2 here, so everything's in balance. So just count your boxes. I have 6, and then here I have 1, sorry about that. It's not the number of nitrogens, it's the number of boxes. 1, and here I have 2 boxes. So 6, 1, 2 is how you do that one. Okay, let's go ahead and do the aluminum and the aluminum chloride. So I'm doing this one over here. So it's Al. I'm going to do this one using the intuitive method. And that's a 3. When you do that, I want you to write the elements down below the arrow and then count the atoms before you get started. So there's 1 aluminum there, there's 1 aluminum there, 2 chlorines there, and 3 chlorines there. So my aluminum's already in balance. Let me get on screen here. My aluminum is already in balance. So I need to work on the chlorine. Now 2 does not go into 3 and 3 does not go into 2. So I need to find the smallest number that they both go into evenly. That number would be 6. So in order to get 3 to multiply up to 6, I have to put a 2 here. So 2 times 3 is 6. And for this one it's a 2, so I have to multiply this by 3 to get it up to 6. So now we have 6 chlorines and 6 chlorines, but in doing that I threw the aluminum out of balance. There's 2 aluminum there and only 1 here, so I simply have to add a 2 over there. Okay, so now we count the atoms after we finish. We have 2 aluminum and 2 aluminum. We have 3 times 2 is 6 chlorine, and 2 times 3 is 6 chlorine. So these outside columns should match up. Everything is in balance, and that's that. All right, let's go ahead and do this last one, this pentane combustion reaction. Combustion reaction is you're burning a hydrocarbon in oxygen, and it produces carbon dioxide and water. That's always true of combustion reactions. The only question is how many moles of each of these do you get? So I'm going to copy the equation a second time here. So C3H6 plus, I believe that should be C3H8, but I'm going to leave it as a 6. Okay, let's balance it as a 6. Plus O2 is going to give us CO2. I'm going to draw a line here so as not to confuse the two. Plus H2O. Okay, we'll do this using the intuitive method. So I got C, H, O. Let's count atoms on both sides. I got 3 carbons. I got 1 carbon. I've got 6 hydrogens. Here I've got 2 hydrogens. I have 2 oxygens. Here I have 2 plus 1 is 3. All right, so let's balance carbon first. So I have 3 on this side, 1 on this side, so I'm going to put a 3 up here. Now, I don't want to go ahead and do anything with oxygen. You want to stay away from oxygen for 2 reasons. It appears in more than one location on one side of the arrow. So on the right side of the arrow, it appears in 2 places. That's going to make it messy to balance. And also, it's a lone element here. You don't want to balance lone elements. They're not attached to anything else. They don't help you to balance anything else. So we skip them until the end. So we did carbon, but we don't want to balance the oxygen yet, so let's go ahead and do hydrogen. We have 6 on this side and 2 on this side, so we're going to multiply this by 3. So 3 times 2 is 6, and 6 there. So hydrogen and carbon is in balance. Now let's see where we are with the oxygens. So we have 3 times 2 is 6, and 3 times 1 is 9. That's a little messy over here, because what it means is I have to have 2 times something is going to give me 9. Since 9 is an odd number, it's a little weird. So the number that will work for that, though, is 9 halves. Okay? So 2 times 9 halves will give me 9. So it'll balance with the 9 over on this side. We didn't have to change this at all, so there's a 1 coefficient there. So my coefficients are 1, 9 halves, 3, and 3. But you're not supposed to have fractions as coefficients. So how do you get rid of that? You multiply everything by 2. So 1 times 2, and I wrote it down here, is 2. So 2 times 1 is 2. 2 times 9 halves is 9. Just do that on a piece of paper off to the side if you don't believe me. So 2 times 9 halves is 2. The 2's cancel out. It becomes 9. 2 times 3 is 6. And 2 times 3 is 6. So these are actually your final coefficients right here. 2, 9, 6, and 6 for that problem. All right. Again, pause, go back if you need help on something else. Now we're going to get on to really the star of this particular session, and that is the dimensional analysis. Okay. So, how many inches, number 5, how many inches in a mile? So there's 2 things there. There's something they're asking for, and there's something they're giving you to get started with. So how many inches is what you're looking for? So you put that way over on the right, and you can just draw a little line, an equal sign, to indicate that that's the unknown. You're trying to find that out as some number of inches. Then what they give you here is a mile. It would have been more properly stated 1 mile. Okay, so it really means a mile, really means 1 mile. So that's way over here on the left. Okay, I haven't filled any of this in yet. So what you have here is your 2 conversion factors. So each one of these you can turn into 2 conversion ratios. So there's 12 inches for every 1 foot, or there's 1 foot for every 12 inches. This first one, A, can turn into either one of those. Those are both true statements. Okay, for the second one, B, there's 5,280 feet for every 1 mile, or 1 mile for every 5,280 feet. Those are both true statements. All right, so what we're going to do is we have to find which ones do we put in to get from 1 mile to some number of inches. Well, we want miles to cancel out because it's not in our final answer, it's inches. So we want miles to go away, so we pick the one that has miles on the bottom. And that's this one right here, 5,280 feet for 1 mile. So that'll make miles cancel with miles. Now on this side we can work backwards. We know we want to end up with inches, so we want the conversion factor that has inches up on the top. And there's only one of these that has that, and it's this one right here. 12 inches for every 1 foot. So we write 12 inches for every 1 foot, so inches ends up here, it goes over to there, and you'll notice that feet cancels out. Foot here cancels with foot there, so miles is canceled out, feet have canceled out, the only thing we have left standing is inches. So we have our units set up properly, so now we're ready to multiply. 1 times 5,280 times 12 divided by 1, divided by 1, and that gives you 63,360 inches in 1 mile. Okay? So that's how you work these problems. Go ahead and do the next one. And so, it's how many centimeters in 4.7 kilometers. So over here we start out with some number of centimeters. We're trying to find some number of centimeters at the end of the problem. This is our solution over here. We're starting us off with 4.7 kilometers. So here we have 2 conversion factors, and we can change A into 2 conversion ratios. There's 100 centimeters for every 1 meter, or there's 1 meter for every 100 centimeters. Those are both true statements. Now we go to B, and we put one over the other. There's 1,000 meters for every 1 kilometer, or there's 1 kilometer for every 1,000 meters. So that's a true statement as well. So of those 4, we have to figure out which ones we need to solve this problem. Well, we want kilometers to cancel out, so we need one with kilometers on the bottom that'll cancel with this kilometer. And the one that does that is this one right here. Finally, we want centimeters in our final answer, so we need the conversion factor that has centimeters on the top in the numerator, so it'll carry over to our answer. And the only one that has centimeters up there is this one, 100 centimeters per meter. So we used 1,000 meters per kilometer for this one, and we used 100 centimeters per meter for this one. And you'll notice kilometers cancel with kilometers and meters canceled with meters. The only thing I have left standing is centimeters. So now I can multiply. 4.7 times 1,000 times 100 divided by everything on the bottom, divided by 1, divided by 1. That gives you 470,000 centimeters. All right, let's keep going. How many inches in 10 meters? This is a crossover type of problem because it involves both metric units and English units or imperial units, but that doesn't matter. The conversions work the same way. So how many inches? So the question's asking for inches. So way down here we have inches. Some number of inches is what we're looking for in 10 meters. So that's what it's starting us off with, 10 meters. So here's our conversions. 1 inch for every 2.54 centimeters. So 1 inch for every 2.54 centimeters, or 2.54 centimeters for every 1 inch. And 100 centimeters for every meter, so 100 centimeters per meter, or 1 meter per 100 centimeters. So now we have to choose which of those 4 conversion ratios we're going to need. Well, we have 10 meters here at the start, so we're going to have meters on the bottom to cancel out. So the only one that has meters on the bottom is this one, 100 centimeters over 1 meter. So meters cancels with meters. And now in the end we need inches, so we need the only one that has inches up on the top here, and that's going to be this one down here, 1 inch for every 2.54 centimeters. So we write that right here. And we notice when we do that, that centimeters here cancels with centimeters here. And so we've had centimeters cancel, meters cancel. And so we multiply 10 times 100 is 1,000. Divided by 2.54, you divide by the things on the bottom. And 1,000 divided by 2.54 is 393.7 inches in 10 meters. All right, so I hope you're starting to see the pattern of these and how you do these. Don't worry, we'll do a lot of them, and you're going to be doing them really for the rest of this class. Okay, let's finish up with our last 2 problems. Let me adjust this a bit so you can see the whole thing. Okay, so this is our Usain Bolt problem. Usain Bolt runs 100 meters in 9.8 seconds. What was his average speed in miles per hour? So you've got 6 conversion factors, so you can convert that into 12 conversion ratios. I'm not going to read them all, but the first one is 1 hour equals 60 minutes. So that means you have 1 hour for every 60 minutes, or 60 minutes for every 1 hour. The next one is 1 minute equals 60 seconds. So you have 1 minute for every 60 seconds, or 60 seconds for every 1 minute, and the rest of them, you can do the rest of them the same way, and I've just lined them all up down here. So let's look at the problem. What is his average speed in miles per hour? So I want to end up with a unit of measure of miles per hour. What does it start us off with? So you kind of have to interpret this. It says he runs 100 meters in 9.58 seconds. So that means he runs 100 meters for every 9.58 seconds that goes by. So it's 100 meters over 9.58 seconds. So what you've got to do is convert meters into miles over here and convert seconds into hours over here. So you break this up into basically two problems within the same problem. Let's deal with the meters and the miles first. So we're going to deal with distance. Those are measures of distance. So what we need to do is find the conversion ratios that cancel, that eventually get us to miles of distance. So we have meters on the top here, so we need one with meters on the bottom. Our first conversion has to have meters on the bottom. If we look along here, there's one. That's the only one. It's 100 centimeters over 1 meter. So that's going to go right here, 100 centimeters for every 1 meter. So meters has canceled out. Now we have centimeters on the top, but that's not in our final answer down here, so we need to get rid of centimeters. So we need one with centimeters on the bottom. So let's look. There's one. There's one. So that's another possibility right there. But the reason that's not a possibility is we've already used that one. We used 100 centimeters for every 1 meter. So that means basically we've eliminated this one, but we've also eliminated that one. Once you've eliminated one of the pair, you eliminate the other one in the pair. So the only one we have then is 1 inch for every 2.54 centimeters right there. Okay, so centimeters cancels with centimeters. Now we have inches, but inches is not in our final answer down here, so we need to get rid of inches. So what has inches on the bottom? There it is right there. But also this one. But we used this one 1 inch equal over 2.54 centimeters already right there. So that means we're going to cancel this one out as well. So the only one that has inches on the bottom is 1 foot for every 12 inches. So inches right here cancels with inches right here. Okay, that means we've used this one. That means we can eliminate this one as well. Finally, we have feet on the top. So we're going to have feet on the bottom. Let's find the only one with feet on the bottom is right here. 1 mile for every 5,280 feet. So we use that one right there. And we see that feet here cancels with feet here. And what we see that we really want to see is this, that miles is on the top, and that's what we want in our final answer. So that means we're done with the distance part of this problem. By the way, we can cancel out both of these because we've used one of them. Now we're going to continue with the same equation, but now we're going to focus on time. So we start off with seconds down here on the bottom. And we don't want seconds in our final answer, we want hours. So we have to have seconds cancel out. So we only have 2 pairs of conversion ratios left. So we need seconds on the top. Well, if I look over here, there's only one of them that has seconds on the top, that's this one. So we come way over here and we write 60 seconds over 1 minute. So this seconds way over here at the beginning of our problem cancels out with this seconds right here. Okay, so that's gone. So that means we've used up both of these. So we only have one left. We have minutes on the bottom here, and we need one with minutes on the top. That's going to be this one. So it's 60 minutes over 1 hour. So minutes cancels with minutes. And the best part is what we end up with on the bottom is what we want on the bottom of our final answer, which is hours. Okay, so we end up with miles on the top, hours on the bottom, and all these numbers. So the way you're going to compute this is 100 times 100 times 1 times 1 times 1 times 60 times 60 divided by 1 divided by 1 divided by 5,280 divided by 12 divided by 2.54 divided by 1 and then finally divided by 9.58. And when you do all of that, you end up with 23.35 miles per hour. It's a big messy one. You won't have any that are that long or complicated in chemistry. But again, we're practicing the skill of dimensional analysis. And that was kind of, I think, a fun problem to know how fast the fastest man in the world was running when he set a world record. Okay, we're going to move on. We're making pretty good time here. This third one is a little bit tricky in that what I'm asking for here. So if 1 meter equals 100 centimeters, how many cubic centimeters, that's read cubic centimeters, is in 1 cubic meter? So the way you simply do that is you write that equation that I gave you, that equality, 1 meter is 100 centimeters, and then you surround it both the number and the unit of measure in parentheses on both sides, and you cube them. So you raise them to the third power. So when you do that, you cube both the number and the unit of measure. That's the point that I want you to get out of how you do this. So 1 to the third power is 1, and meters cubed is meters cubed. Okay, over here on this side, you have 100 to the third power is 1 million, and centimeters cubed is centimeters cubed. So 1 cubic meter, that's a meter high by a meter wide by a meter deep, that's a box, 1 meter by 1 meter by 1 meter, is going to be 1 million cubic centimeters. So cube both the number and the unit of measure. Okay, let's finish up down here. This one's not too different from Usain Bolt. It's just a lot of conversions. The tricky part, I think, is at the beginning, deciding what the question's asking for and what it gives you. So I'm going to skip right to that part. The question is this: how many golf balls are in a warehouse that is half full? So way over here on the right, we're looking for some number of golf balls. And way over here on the left, we're given a number. It's a half full warehouse. So you can think of that as half a warehouse. Okay, so half a warehouse is what we start with. Number of golf balls is what we end with. And everything you see up here above are conversion factors. So here you have one box equals 8 golf balls. So I wrote that as 2 conversion ratios. One box for every 8 golf balls, or 8 golf balls for every 1 box. The next sentence: a crate of golf balls, that means one crate of golf balls contains 232 boxes. So one crate for every 32 boxes, or 32 boxes for every 1 crate. That's right there. Now we go, a truckload can hold 144 crates. So I say one truck, meaning truckload, for every 144 crates, or 144 crates for every 1 truckload. And finally, a warehouse can hold 25 truckloads. So one warehouse for every 25 truckloads, or 25 truckloads for every 1 warehouse. So we have in total 8 different conversion ratios there to work with. So what do we start with? Well, we're starting over here with half a warehouse. The word warehouse is on the top. So we need one of the conversion ratios with warehouse on the bottom. So we look for that, and there it is. That's the only one. So we multiply that by 25 truckloads for every 1 warehouse. Now, if we start over on this side, we want some number of golf balls. That means we need golf balls in the numerator of our final conversion. So where do we find that? Well, we come along. There it is right there. There's nowhere else where you find that. So it's 8 golf balls for every 1 box. So that's going to be our conversion there. So we've done this conversion ratio and this one. Now we got to find the 2 in between. Well, we know truck is not in our final unit of measure answer down here. So we need to get rid of truck. So we need truck. If it's on the top here, we need it on the bottom. So where is truck on the bottom? Right there. It's actually 2 different places. But remember what I said, when we use one of these conversions, we use 25 trucks per warehouse. We use that one, so that means we get rid of the one that goes along with it. There, those 2 go together. So the only other place we see truck on the bottom is 144 crates per truck, so right there. So truck cancels with truck. We already had warehouse cancel with warehouse. Now we've got to get rid of crates because that doesn't appear in our final answer. So, and by the way, I should have crossed this out now. I used that one, so that means I also crossed this one out. Okay, now we got to get rid of crate, so we need crate in the denominator. Where is it? Right there. 32 boxes per crate. So I'm going to write that right there. That means that crate cancels with crate there. That's all good. And since we use this one, we cross it out, and we also cross out its partner right there. Finally, we only have one left. We have box on the top, so we need box on the bottom. So this one right here gives us that, box on the bottom. So it's 8 golf balls per box. So we've used this one and this one. So now we cancel box with box. So our units line up. Warehouse cancels with warehouse, truck with truck, crate with crate, box with box. You end up with golf balls, which is in your final answer. So now you have your units lined up properly, so you do the math. So it's 1 times 25 times 144 times 32 times 8 divided by this 2 on the bottom here, divided by 1, divided by 1, divided by 1, divided by 1. And when you multiply all of that and do all those multiplications and divisions, you end up with 460,800 golf balls in this situation. Okay, so that's the end of this problem set. That was the one we did in class. So here's all the solutions. You should be ready to turn this in at the beginning of class. If you really have a question about something, go ahead and ask me. And I'm going to have one more quick assignment for you tonight. I'm going to read through some notes And I'd like you to listen to this, and I didn't give you this assignment. Actually, I take it back. We're just going to do it in class tomorrow. I decided that's why I didn't give it to you today. So this is all you need to do tonight, and we'll see you in class tomorrow and continue from there. Have a good evening.